values, and I want to make sure that no information flows from true values in the future that I haven't generated yet. And so that's what this is. That's what this positional mask is saying. It's saying when I'm outputting stuff at position 0, I can only look at stuff at position 0. When I'm outputting stuff at position 1, I can look at stuff at position 0 or position 1, etc. So you can only ever look backwards in time. This is like time 0, I guess you could say. It's like making sure that it's causal. Okay, let's look at attention. So here's their implementation of attention. So this is the figure and this is the equation. So here's their little attention thing. You have the query, you have a key, and you have a value, and possibly a mask. And so you go ahead and implement essentially exactly what we talked about. So there's a matrix multiply between the query and the key transpose. We're dividing by dk. We're then taking that and we're softmaxing it. And then we're doing a final matrix multiply between the values and the computed attention weights. So just a couple lines of code to implement their attention mechanism. Again, what I really like about the way they've set this up is this little chunk of Python code can be used multiple places throughout the architecture. Okay? And then, so this is one little bit of attention. They actually use something called multi-headed attention. So we haven't really talked about this, but the idea is if you imagine that we're trying to translate a sentence and we're looking back into something in the past, what we've talked about is single-headed attention, where we use some sort of comparison function to generate weights, and then we sum things together to give ourselves a context vector that we then use to generate some new output. Multi-headed attention is exactly what it sounds like. We just do that multiple times. The advantage of this is that it allows each of the heads, so think of these as like read-write heads or something on a hard drive, where each one can be looking at different things. Each head is allowed to specialize to look for a certain kind of information. And that is easier apparently to train than having one giant head that somehow learns to extract all of the information it might ever need. So you could imagine that one head is really, really good at counting nouns, and another head is really, really good at dereferencing pronouns, and another head is really, really good at looking for gendered things, etc. So they can all kind of specialize in some aspect of your problem. So how do you do that? Well, in the paper they talk about concatenating multiple things together. So they create a generic multi-headed attention class where the forward pass, again you have queries, keys, and values. And this is a little bit more complicated. We're not going to take the time to understand it in detail, but you can kind of imagine essentially what they do is they just do a bunch of attention on a bunch of things all at once. And then they concatenate the results together. Okay? Finally, there's a really clean implementation of position-wise feed-forward network. So this is super simple. We all sort of know and love this already. So you calculate some sort of X, you go through a weight matrix, you do a value, you drop out, and another weight matrix. So this is a basic feed-forward, fully connected feed-forward chunk. And that is, I'll show you the picture. That is this bluish box here. So everywhere it says feed-forward. Okay, so given all of those pieces, you can begin to, and positional encodings and some embeddings things. Given all those pieces, you can put them together and you can begin to make a full model. And so you can sort of see how they put all the pieces together. So they're going to instantiate a generic encoder-decoder. They're going to pass in an encoder, which consists of an encoder layer, which consists of a decoder, it's a D model, the dimension of the model, so that's 512, as well as they're going to copy the attention bit, they're going to copy the feed-forward bit, and they have some dropout thing. And they're going to create a decoder layer, and they got some embeddings things, and this generator. And that's it. So I think it's a very clean setup there. I really liked it. Yes?
What is the positional encodings? How does that work?
Yeah, so the idea here was if you want your neural net to be able to take advantage of positions, remember we've got rid of positional information. Because everything is just transforming from one layer to the next, you could imagine, if you didn't have the positional encodings, you could imagine taking your input sentence, permuting the words arbitrarily, and you get exactly the same answer. So the positional encoding puts back, it sort of like puts time back into the sequence. And it lets the neural net say, I really need to know if this word came before this word or after this word. Like it can do a comparison based on their relative encodings. But how do you represent time? And the answer is, well, you could imagine like a number or like a scalar value, but here they're using a feature vector to represent time. And they're doing it by decomposing time into a sequence of, by using the sequence of sines and cosines. The stated reason for this is, in the paper is that if you train on specific numbers, you might not generalize if your sentences get longer than what you've trained on. So in training, you're only going to see sentences up to a certain length. And so but you really would like to generalize to longer sentences. And so this is an attempt to be a representation that will generalize well. So if I've kind of learned the pattern up to a certain amount, I want to be able to extrapolate. And because this is periodic, the thinking is that you'll be able to extrapolate better. Whereas if it was linear, who knows what would happen. Yeah, so it's a clever idea. Probably pretty important. Okay, so finally, you start training. There's tons of stuff in here about training. So your job in the lab is to go ahead and figure out where in here you stick the general confidence data set. Again, use the Colab version of this, not the rest of it. Okay, hopefully that's helpful. We're out of time. Any final questions before we break?